The final exam on linear algebra from fall 2018 contains the 3 parts. We are going to go through all of the 3 parts. The first part starts from the question on vectors and vector operations. So we need to find the 2 vectors, u minus v and u plus 2v. So let's find the u plus 2v. So in order to do this, we need to add the u and 2v. So 2v is going to obtain by multiplying the 2 to all the components of this vector v, which is going to be 0, 4, 2, and 0. It's going to be 2, 5, plus 1, and 2. So if we multiply these 2 vectors as a scalar multiplication, it's going to be 4 minus 5 minus 2 plus 4, which is going to be plus 1. So please note that your solutions and the answers both should be correct to get the credits on this section. So in the second problem, we are given the 2 matrices P and Q. We know they are determinants. We need to find the determinant of the 3 multiplied as the P transpose and Q inverse. It's going to be determinant of the 3i multiplied as the determinant of the P transposed multiplied as the determinant of the Q inverse. So the determinant of the 3i, where I is 4 by 4 matrix, is going to be 3 in the power of 4 multiplied to the determinant of the P transpose is simply equal to the determinant of the P, and determinant of the Q inverse is going to be a reciprocal of the determinant of the Q. It's going to be 1 over 3, so which is going to be 3 in the power of 3 multiplied to the 4, or 27 multiplied to the 4, which is 108. So the answer here is 108. So on the question number 3, we need to find the 2 values for the lambda and mu so that these 2 vectors are parallel. So since here we've got a 0, lambda should be also 0, and we see that the mu should be twice smaller than the value of the 1. Since 2 is twice smaller than the 4, so mu should be equal to the 1 over 2. So if you set the lambda to be equal to the 0 and mu to be equal to the 1, these 2 vectors become parallel. So in the question number 4, we need to multiply these 2 matrices. So please note that the columns of this matrix A, or the rows of this matrix A, are orthogonal to each other. It means that when we multiply the rows or the columns of this matrix to each other, we're going to get the zeros. So when we multiply the first row to the first column, it's going to be simply the length of this vector, which is 1 in the square plus 2 in the square plus minus 5 in the square, which is going to be equal to the 30. So please note that when we multiply this row to this column, we are going to get exactly 0. It's going to be 0 and 0. So here, when we multiply this row to the second column now, it is going to be the length of this vector now, which is going to be minus 2 in the square plus 1 in the square plus 0 in the square, which is going to be 5. And the length of the last vector is going to be 1 in the square plus 2 in the square plus 1 in the square. It's going to be 6. So all the other terms are 0, since when we multiply the orthogonal vectors to each other, we will get 0. On the question number 5, we need to find the eigenvalues of the a squared. So what we can do is we can multiply the a to itself and then find its eigenvalues, or we can find the eigenvalues of this matrix and square them. So the sum of the eigenvalues of this matrix should be equal to the trace of this matrix, which is equal to the 4, and the multiplication is equal to the determinant, which is going to be 4 minus 1 multiplied to the minus 1. So which is going to be simply equal to the 3. So the eigenvalues are 3 and 1. And their squares are going to be 9 and 1. So the eigenvalues of the a square is equal to the 9 and 1. So let's go through the questions from the second part. So this part contains 10 questions, and please note that in order to get the full credit, you need to prove the statement if this is true and give a counterexample if this is false. So that lambda is an eigenvalue of the a, then lambda square is an eigenvalue of the a square. So there was an example from the last question of the previous part, but this is not enough to just give an example if the statement is true, since conditions it is necessary to prove this. So the eigenvalue problem for the matrices is written as A multiplied to the x should be equal to the lambda multiplied to the x. So now we are going to multiply the A to the ax, or simply ax squared, a squared multiplied to the x. So at the same time, we know that ax is equal to the lambda x, right? So we are going to substitute the ax with the lambda x, right? So since lambda is a constant, we can take this out from this bracket. It's going to be lambda multiplied to the ax. So we know that ax is still lambda is multiplied to the x, which is going to be lambda multiplied to the lambda x, which is going to be lambda square x. So from the left hand side, we've got a squared multiplied to the x. From the right hand side, we've got lambda squared multiplied to the x, which shows that the lambda square is the eigenvalue of the a square. So question number 2, if the lambda is equal to the 0, then rank of the matrix is equal to the n, which is false, because if the multiplication of all the eigenvalues is equal to the determinant of the matrix, and if one of them is equal to the 0, it means that determinant is equal to the 0. It means that the matrix has dependent columns. So we know that the rank is the number of the independent columns, right? So this is going to be less than n if the determinant is equal to the 0. Or we can just give a counterexample. So for example, so we know that for the upper triangular matrices, the eigenvalues are on the diagonal, or we can just draw this matrix. So for this matrix, the first eigenvalue is equal to the 1, the second one is equal to the 0, and we see that the rank of this matrix is equal to the 1 because there is only one pivot column in this matrix. So the third question tells us that determinant of the 4a is equal to the 4 multiplied to the determinant of the a, which is false in general because we know that determinant of the 4a is equal to the 4 in the power of n multiplied to the determinant of the a, where n is the matrix, is the size of this matrix A. So depending on the size of the matrix A, so this n is going to be different. So for example, when n is equal to the 2, determinant of the 4a is equal to the 16 multiplied to the determinant of the a. But in general, this is false. So if a is not invertible, then ab is not invertible neither. So this statement is true, and we're going to prove this in the following way. So we know that if a is not invertible, it means that its determinant to the 0. So the basically matrix is not invertible when its determinant is equal to the 0. So let's find the determinant of the AB, which is going to be determinant of the A multiplied to the determinant of the B, so which is going to be still 0 since determinant of the A is equal to the 0. Since determinant of the AB is equal to the 0, it means that AB is not invertible. So if U is orthogonal to the V and omega, then U, V and omega are always parallel, which is false, and we can give a counterexample, which is the simple one, was the case of the ij case. So this is I, j, and k vectors, right? So this k vector is orthogonal to j and I, for example, and these two vectors j and I are not parallel, or we can rename these vectors. So let's say this is u, this is v and omega. So u is perpendicular, orthogonal to the v and omega, where v and omega are not parallel. So this is false in general, and it is enough to give a counterexample. So if u and v are perpendicular unit vectors, then the norm of the u minus v is the square root of t, which is true. And we can prove this. So the norm of the u minus v in the square is equal to the u minus v transpose multiplied to the u minus v, and we can open up the brackets. It's going to be u transpose to the u minus 2 u transpose to the v plus V transposes a V. So the U transposes a V is equal to the 0 since U is orthogonal to the V. So the U transposes a U is the norm of the U in the square plus V transposes the V, it's the norm of the V in the square. Since the U and V are the unit vectors, their norms are equal to the 1, it is going to be 1 plus 1, which is equal to the 2. So the U minus V in the square is equal to the 2. It means that the U minus V, its norm, is equal to the square root of 2. Question number 7. If A is a 4 by 4 square matrix with a row of zeros, then A is not invertible, which is true. It means that if A is a matrix which has 0 rows, then its determinant is equal to the 0. So when the determinant of the matrix is equal to the 0, A is not invertible. So every matrix with 1s on all entries below the main diagonal is invertible, which is false. And we can give a counterexample. For example, 1, 0, 1, or like 0, 0, the easy example, right? So this matrix has 1, all entries below the diagonal is equal to the 1, its determinant is equal to the 0, so that is why this matrix is not invertible. So A, B, C are symmetric, then transpose of the A, B, C is equal to the CBA. So the transpose of the multiplication of the 3 matrices is the multiplication of the transposes in reverse order. It's going to be C transposed, B transposed, and A transposed. So the 2 matrices, or a matrix, is called the symmetric matrix if A transpose is equal to the A, B transpose is equal to the B, and C transpose is equal to the C. So this is going to be CBA. So it means that this is true. So any square matrix has no free variables, which is false because it is possible that a square matrix has a free variable. For example, 1, 0, 0, 0. So this matrix has a free variable. Sixth and second column is the free column. So now let's go through the problems from the second part. So we need to bring this matrix to the row echelon form. So in order to do this, we are going to add the first row to the second. So please note that the first row is going to be the same. Second row is going to be 0, 3, 4. So now we need to get rid of this 1 here. So in order to do this, we multiply the first row to the minus 1 and add this to the third one. So this entry is going to be multiplied to the minus 1. This entry is going to be multiplied to the minus 1. And when we add this to the third row, it's going to be 0, 3, and 4. So now we're going to multiply the second row to the minus 1 and add this to the third one. It's going to be 1, 2, 0, 0, 3, 4, 0, 0, 0. It is already on the row echelon form. So A is not invertible since its determinant is equal to the multiplication of its diagonal entries, which is 1 multiplied to the 3 multiplied to the 0, which is equal to the 0. So we need to solve the homogeneous system of linear equations. So we basically need to write down the row echelon form of this matrix. We need to multiply this to the vector which contains the 3 components x1, x2, and x3 and equalize this to the 0. So it's going to be 0, 0, and 0. So since the third column does not have a pivot, it is going to be a free column. It means that we need to set the third variable x3 to be equal to the 1. And then we need to solve the second system. So the second system tells us that, so we need to multiply the 3 to the x2 plus 4 to the x3 and equalize this to the 0. So when we set the x3 to be equal to the 1, we can find that x2 should be equal to the minus 4 over 3. Now we need to put these two values to the first equation, which is x1 plus 2x2 is equal to the 0. When we set the x2 to be equal to the minus 4 over 3, it gives us that x1 is equal to the plus 8 over 3. So this is the spatial solution for the system in general. So the solution space of this system of linear equation contains all possible linear combinations of this vector. So basically it is going to be x multiplied to the 8 over 3 minus 4 over 3 and 1 multiplied to the parameter t, where t takes any value from the real numbers. So let's consider the second problem. So in this problem, we need to find the SVD composition of the matrix. So we first of all are going to multiply the A to its transpose. It's going to be 1, 1 and 0, 0, 2, 1. If you multiply this, it is going to be the length of the first matrix, which is 2. So the first row to the second, it's going to be 2. The second row to the first column, it's going to be 2. The length of the second row, it's going to be equal to the 5. So in the second part, we need to find the eigenvalues of this matrix. We call this as the singular values of the A. So the sum of the two eigenvalues is equal to the 7, which is the trace of this matrix. And the multiplication of the eigenvalues is equal to the determinant, which is 2 multiplied to the 5 minus 2 multiplied to the 2, which is going to be 10 minus 4, which is 6. So it's clear that the first eigenvalue is equal to the 6 and the second one is equal to the 1. So the singular values are the square root of 6 and 1. So we need the singular values in order to build the SVD decomposition. So now we need to find the orthonormal eigenvectors U1 and U2 of the A transpose. In order to do this, so we need to subtract so eigenvalue, the first eigenvalue, which is 6, multiplied as identity from the AA transpose matrix, which is 2, 2, 2, 5. So basically we need to subtract 6 from the diagonal entries of this matrix, which is going to be minus 4, 2, 2, minus 1. So we need to, so to which vector we need to multiply this matrix in order to get a 0 and 0, which is going to be 1 and 2. Right? So if we multiply the second column to the 2 and the first column to the 1 and add them, we will get 0 and 0. So now we need to normalize this. It is going to be, so x1 divided to its norm, the norm of this vector x1, it's going to be 1 in the square plus 2 in the square from the square root, which is going to be square root of 5. It's going to be 1 over square root of 5 and 2 over square root of 5. So in order to find the second eigenvector, so we are going to subtract lambda 2, which is 1 multiplied as identity from the AA transpose, which is 2, 2, 2, 5. If you subtract the 1 from its diagonal entries, it's going to be 1, 2, 2, 4. So we are going to multiply the first column to the minus 2, the second column to the 1, and add them in order to get a 0 and 0. So if we normalize it, it's going to be minus 2 over square root of 5 and 1 over square root of 5. So now we need to find the two orthogonal eigenvectors of the A transpose to the A, and we can find this by multiplying the A transpose to the x1 and x2. So the A transpose was 1, 1, 0, 0, 2, 1. It is enough to just multiply this to the x1, which is 1 and 2, since we are going to normalize this anyway. So 1 and 2, it means that the first column is multiplied to the 1, second column is multiplied to the 2, and we need to add them. So it's going to be 1, 5, and 2. Right? So the A transpose is going to be multiplied to the second eigenvector as well, which is minus 2 and 1. So the first column is multiplied to the minus 2, the second column multiplied to the 1, which is going to be minus 2, 0, and 1. So now we need to normalize this. In order to do this, we need to divide this vector to its norm. The norm of this vector is 1 in the square plus 5 in the square plus 2 in the square, which is going to be square root of 30. It's going to be 1 over square root of 30, 5 over square root of 30, and 2 over square root of 30. So we are going to divide the length of this vector to itself. It's going to be minus 2 over square root of 5, 0, 1 over square root of 5. So please note that V1 and V2 should be orthogonal to each other in unit. So in the last part, we need to find a V3, which is going to be orthogonal to the V1 and V2. So we set the components of the V3 as A, B, and C. And we are going to find the values for the A, B, C so that V3 is perpendicular to the V1 and V2. So basically V1 transposes the V3 is equal to the 1, 5, 2 multiplied to the A, B, C is equal to the 0. And V2 transposes the V3, which is minus 2, 0, and 1, multiplied to the A, B, C is equal to the 0 as well. So it's going to be A plus 5B plus 2C is equal to the 0, minus 2A plus C is equal to the 0. So we can find that the C is equal to the TA. So since there are three variables and two equations, we can set one of the variables to be equal to any value. For example, A can be equal to the 1, then C is equal to the 2. If we substitute this 1 and 2 to the first equation, it's going to be 1 plus 5B plus 2 multiplied to the 2 is equal to the 0. So 1 plus 4, it is 5 if it goes to the right hand side part. So B is going to be equal to the minus 1. So the V3 is going to be equal to this vector, which is 1 minus 1 and 2 divided to its norm. So the norm of this vector is 1 and a square plus minus 1 and a square plus 2 and a square, which is going to be square root of 6. It's going to be 1 over square root of 6 minus 1 over square root of 6 and 2 over square root of 6. So this vector now is unit, and indeed if we multiply this vector to V1 and V2, it is going to be equal to the 0. Let's consider the problem from the third part of the section. So we need to solve the system of linear equations using the Cramer's rule. In order to do this, we need to be able to find the determinants very well. First of all, we're going to create a coefficient matrix. It is going to be 1, 1, 1, 2, minus 1, 0, 4, 0, minus 1. So first of all, we need to find the determinant of the A, which is going to be 1, 1, 1, 2, minus 1, 0, 4, 0, minus 1. So we are going to go through the entries on the third column. It's going to be 4 multiplied to the cofactor C3, 1, minus 1 multiplied to the cofactor C3, 3. So let's find the cofactor C3, 1, which is going to be the determinant of the matrix. When we eliminate the third row in the first column, it is going to be 1 multiplied to the 0 minus 1 multiplied to the minus 1, which is going to be equal to the 1. C3, 3 is going to be equal to the determinant of the matrix when we are going to eliminate the third column and the third row, which is going to be 2 multiplied to the minus 1 is minus 1, minus 1 multiplied to the minus 2 is going to be minus 2, which is minus 3. If we set this 2 values to here, it's going to be 4 multiplied to the 1, minus 1 multiplied to the minus 3, which is going to be equal to the 7 exactly. So now we're going to find the x1, x2 and x3 using the so-called Cramer's rule. In order to do this, we need to find the determinant of the B1 and divide this as the determinant of the A. Determinant of the B1, so B1 matrix is obtained by substituting the first column of the A with the right hand side part, which is 1, 0 and 0 here. So we are going to substitute 1, 0 and 0 was the first column of the matrix A. So 1 minus 1, 0, 1, 0, minus 1. So the determinant of this matrix can be found by going through the first column. So we are going to just simply multiply 1 to the determinant of this matrix, which is equal to the 1. So the determinant of this matrix is equal to the 1. So that is why the x1 is going to be equal to the 1 over 7. So now we are going to substitute the second column of this matrix A was the right hand side part. It's going to be 1, 2, 4, 1, 0, 0, 1, 0, minus 1. Again, we're going to go through the second column. That is going to be 1 multiplied to its cofactor, which is C1, 2. So the C12 is equal to the minus 1 in the power of 1 plus 2 multiplied to the determinant of the matrix when we are going to eliminate the first row and the second column. It's going to be 2, 0, 4, minus 1, which is going to be minus 1 multiplied to the minus 2, or simply 2. So the x2 is going to be 2 over 7. So now in order to find the x3, we are going to substitute the right hand side part with the third column. So instead of third column, we're going to write 1, 0, and 0. So we are going to go through the third column. So it is going to be 1 multiplied to its cofactor, 1, 3. So the C3, 1, 1, 3, sorry. It's going to be minus 1 in the power of 1 plus 3 multiplied to the determinant, 2, minus 1, 4, and 0. It's going to be 2 multiplied to the 0 minus 1 multiplied to the 4, which is going to be simply 4. So x3 is going to be 4 over 7. The last problem is about a Qr decomposition. So first of all, need to find the two columns of the Q matrix, which is orthogonal matrix. So we set the small vector A to be equal to the first column of the M, which is going to be 1, 0, 1. To find the small vector B, it's going to be B minus A transpose to the B divided to the A transpose to the A multiplied to the A. So B is 0, 1, 2 minus, when we multiply this T vector, it's going to be 1 multiplied to the 0, 0 multiplied to the 1, 1 multiplied to the 2, it's going to be 2, divided to the A transpose to the A, which is going to be the norm of this vector in the square, which is going to be 1 in the square, plus 0 in the square, plus 1 in the square, which is going to be, again, 2. We need to multiply this to the A, which is 1, 0, 1. If we subtract, it is going to be minus 1, 1 minus 0, it's 1, 2 minus 1, it's 1. So the Q1, it's going to be A divided to its norm. So this is going to be 1 over square root of 2, 0, 1 over square root of 2. And Q2, it's going to be B divided to its norm. It's going to be minus 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. So in order to find the R matrix from the Qr decomposition, so we just need to multiply the Q transposed. So we basically write down the first column of the Q as the first row. It's going to be 1 over square root of 2, 0, 1 over square root of 2. The second column as the second row, it's going to be minus 1 over square root of 3, 1 over square root of 3, 1 over square root of 3, to the M matrix, which is 1, 0, 1, 0, 1, 2. So let's multiply the first row to the first column. It's going to be 2 over square root of 2. The first row to the second column, it's going to be 1 to the 0, 0 to the 1. This one multiplied to the 2, it's going to be 2 over square root of 2. So this row to this column, it's going to be simply 0. Since this multiplied to the 1 and this multiplied to the minus 1, they are going to be the same. So this row multiplied to the second column, it's going to be 3 over square root of 3. Or simply we can write as square root of 2. Square root of 2, 0, square root of 3. So this is the tricks. So now, in order to find the least squared solution for this system mx is equal to the b, we can simply substitute the m with its Qr decomposition. It's going to be Qrx is equal to the b. We are going to multiply both of the sides to the Q transpose. It is going to be Rx is equal to the Q transpose to the b, and we need to solve the system. So first of all, let's find the Q transpose to the b, so which is going to be 1 over square root of 2, 0, 1 over square root of 2, minus 1 over square root of 3, 1 over square root of 3, 1 over square root of 3, multiplied to the b. So b is the right-hand side of this matrix, is given as the 0, 1, and 2. 0, 1, and 2. So the first row to this matrix is going to be this one to the 0, this one to the 0, this one to the 2. It's going to be 2 over square root of 2. And this row to this matrix is going to be 3 over square root of 3. Or simply, this is going to be square root of 2 and square root of 3. So now we need to write down the Rx is equal to this vector. R was square root of 2, square root of 2, 0, square root of 3, multiplied to the x1 and x2 is equal to square root of 2 and square root of 3. So the second equation tells us that when we multiply the x2 to the square root of 3, it should be equal to the square root of 3. It means that x2 is equal to the 1. So now we need to substitute this to the first equation, which is square root of 2 multiplied as x1 plus square root of 2 multiplied as 1 is equal to the square root of 2. So we can cancel these two values. It means that x1 is equal to the 0. So the least squared solution is 0 and 1. So this is the solutions for all the problems.